Hello everyone, today let's solve the problem number 202, happy number. So what the question states here, a happy number is defined by the following process. Start with a positive integer n. So we have to start with a positive integer n equals 19 they have given here. Just for the sake I'm telling, start with a positive integer n, replace n with the sum of square of its digits. You can clearly see here, sum of square of digits. So here start with a positive integer n, replace n with the sum of square of its digits. You can clearly see 1 square plus 9 square 82 that they have given. So just for the example sake I'm considering this one. Replace n with the sum of square of its digits. Repeats this process until n becomes 1. You can clearly see here. So they have repeated the process until this one. N becomes 1. So the product will take this one. 82 here, 8 square plus 2 square, nothing but 8 square here, 2 square. Again this one is 68, the sum of the product, 8 square plus 2 square 68. Again we'll consider 68 product. So we will take the square of it and we will sum this one, sum up this one. 6 square plus 8 square is nothing but the 100. You can clearly see here 1 0 0, nothing but 1 we got here as product. So we have to stop and when we get 1, right? So repeat this process until n becomes 1. If it falls into a cycle that never reaches 1, then it's not a happy number. Here it doesn't fall to the cycle. It doesn't fall into the cycle here because we got the output as 1 here, right? So here we will return this one as true, boolean value true in this case, right? So it is a happy number here in 9 10. So in this case, let's come to the example 2 as well. N equals 2 they have given. So in this case, if you square this one, 2 square will be 4, 4 square will be 16, 16 square 1 square, and 6 square. We will go on considering that one. So output will never be 1 in this case. So output will never be 1 in this case. In this case we have to return false, boolean value false. So that's what they have given in the question, right? So I hope the question is completely clear. What is a happy number and what is not a happy number and what we need to return, right? Either we are going with a boolean value true or false. So suppose if we get the value as 1, then we have to return true, and if we don't get the value as 1 at all, then we have to return value as false, right? So that's what we'll be doing here. So happy number and the not a happy number. I hope this is completely clear. So let's discuss initially. Let's go with the approach. So then let's discuss the edge cases one by one, followed by the this one. Let's finally discuss the code, and let's discuss the complexity of the code that we have written at last. So initially what we'll do, let's discuss the approach. Here you can clearly see the approach that we went with here as Floyd's cycle detection algorithm. You can clearly see here, right? So n equals 19, the first example itself that they have given in the question, that's what I've considered same thing here, so that it will be easier to understand, right? So output that we need to get here is true. So we will be going with tortoise and hare algorithm or Floyd cycle detection algorithm. Floyd cycle detection algorithm, the another name of that one is tortoise and hare algorithm. So we have used this one to detect cycle and for other problems as well, right? So in the linked list, if you remember, so the same thing we'll be using here. So first thing here is let's discuss the step by step. Let's go with step by step explanation here. We'll be making use of 2 pointers. So first one is we'll be going with the slow pointer, and we'll be going with the fast pointers. 2 pointers, slow and fast, will be making use of. So slow here moves 1 point at a time. Slow pointer moves 1 point at a time, and fast pointer moves 2 points at a time. So slow pointer moves 1 point at a time, and fast pointer moves 2 steps at a time. One moves 1 step at a time, and this one moves 2 steps at a time. So if there is a cycle, then both pointers meet at the same number. If there is a cycle, then both pointers meet at certain number, right? So if there is a cycle, then both pointers meet at a certain number. If n reaches 1, then it's a happy number. We know this one, right? We have discussed this one while discussing the first and second example that they have given in the question. If n reaches 1, then it's a happy number. If n doesn't reach 1, then not a happy number. So if n reaches 1, it's a happy number. Doesn't reach 1, then it's not a happy number. So I hope this is clear. So this is the approach that we will be going with. So we will be going with the 2 pointers. One is slow and fast pointer. If there is a cycle, then both the pointers meet at same number. If n reaches 1, it's a happy number. If there is a cycle, then it reaches 1. If there is no cycle, then it is not a happy number. In that way we can say, right? So here let's discuss the same first example. First, what we will do, n equals 19. This example we are considering first example. Here you can clearly see n equals 19. So in this case we will compute the sum of square of digits. So here 1 square plus 9 square we are considering. 1 plus 81, this will be 82, right? So here this will be 8 square plus 2 square. Because we have got the product, again we'll consider this one, this product. Again we will square this one and sum this one up. So 8 square plus 2 square here, 64 plus 4, nothing but 68 in this case, right? So we will consider 68 again here. 68, we are computing for 68 here. 6 square plus 8 square, again 36 plus 64, that leads to 100 here. In this case we will consider 100. 100, we know this one, 1 square plus 0 square plus 0 square, this is 1. 1 plus 0 plus 0, nothing but in this case we will get the output 1. Since we reached 1, 19 is a happy number in this case. Since we reached this one, 19 is a happy number in this case. So this is the approach. So this is the approach that will be going with. So mainly just remember, we are going with the tortoise and hare algorithm, right? Or we are going with the Floyd's cycle detection algorithm. We are going with slow and fast pointer. This one moves one step at a time and this moves 2 steps at a time. If there is a cycle, both pointers meet the same number. If n reaches 1, then it's a happy number. In this case, n is reaching 1. You can clearly see here in the fourth step, when we are computing for 100, it is reaching 1. So since we have reached 1, or since we reached 1, 19 is a happy number in this case, right? So final output we need to return here as true in this case. Boolean value true in this case. If n is a happy number, we are returning true, else we will return false. In this case we have written true. Suppose if we consider the second example, so we would have return false. In that case we have already discussed that one, right? So this is the approach that we will be going with. I hope all the edge cases I hope the approach is completely clear. Let's discuss the edge cases one by one. First edge case here is we are considering n equals 1. Output will be here, in this case output will be true. Why the output is true here? We already have 1 here, so it's an happy number in this case. So here let's consider n equals 2. Output will be false. So we already saw this one in the example 2 in the question itself, right? So this falls into a cycle. You can go on, sorry, while explaining the approach, I said if it falls into a cycle, then we have to return false, not true. So that one I got confused there. If the number falls into the cycle, that doesn't lead to 1 at all at the end. So we have to return false in that case. Here you can clearly see we will do 2 square, next 4 square, it will be 16. 1 square plus 1 square plus 6 square, nothing but 1 plus 36, 37. So 37, 3 square plus 7 square, here in this case 9 plus 49, right? 9 plus 49 is nothing but in this case 58. This goes on 58, 89, 145, 42, 20 and 4. So 4 here, this leads to the cycle here. 4, this leads to the cycle. It will never reach 1 at any cost. So it's not a happy number in this case. Not a happy number. This leads to cycle here. You can clearly see this leads to cycle 4 again. So here, so this will never reach 1. In this case, this is not a happy number. So let's come to the third example. N equals this one lakh we have considered here, the big number, right? So here in this case, it quickly reaches 1, so it's a happy number. So this one this will lead to 0 plus 0 plus 0 plus 0 plus 0 here. Square this up. So first itself we will get 1. So again, well, squaring the number 1, we will get 1 itself. We have already reached 1. This will be true in this case. So it quickly reaches 1 here. So output will be true. So I hope this is completely clear, the edge case and the approach. So we have discussed the approach initially by taking the first example, and also we have discussed all the edge cases that we need to keep in mind. I hope the approach and edge cases are completely clear. Now what we will do, we will try to write the code. Let's try writing. Here the first step here is what we will do, we will initialize slow and fast pointers. We have already discussed this one. Let's slow equals n I'll give, and also fast equals let me give square sum here. We have to square this one, right? Square sum of n. So here we are considering this one, what do you call, helper function, square sum. So let's write the square sum function completely. So here square sum of num here, this one. So this is fine. So here in this case what we will do, let's make use of the variable sum and initialize this one to the 0 variable to store sum of squares. Here in this case, let sum equals 0, and let's loop this one until the number becomes 0. So here while of num, then what we will do, we will add square of last digit. We have to. So this one we saw this one, right? So this one we saw this one by considering the first example and second example. That's what we are articulating this one in the form of code. That's it. So we will, what we'll do, sum equals sum plus number module 10 to the power of 2. So this is exponential operator, double square, this one, right? Double into. So we are adding the square of last digits here. Then we have to remove the last digit. How can we do that? Or how can we articulate that one in the form of code? I'll be making use of double tilde operator here. Num by 10. So you can just dry run the code if you didn't understand. So just dry run this code by considering first example. Again, you'll understand this one very quickly. So this is the math, simple math, right? This one, this is simple math. This is fine. This was asked in one of the companies too as well in the interview for me. So you can just dry run the code using the first example or the second example. So you'll get the output. So you can just consider n equals 19 and n equals 2. Try dry running the code. Here we have successfully written the square sum function here. So here let's come to the main function. We are making use of the square sum function here, right? So the next step in the main function here is we have to loop until fast reaches 1 or cycle is detected. So if cycle is detected, then in this case cycle was detected, right? So it will not be an happy number in this case. So that's what we have to articulate that one in the form of code. So we are making use of tortoise and hare algorithm, right? So I'll just give here fast not equal to 1 and slow not equal to fast in this case. So what we will do in this case, we will move slow by 1 step in the next line. Here square sum of this one slow. This is fine. After moving the slow by 1 step, we have to move the fast by 2 steps. Algorithm states that itself, right? So we have to move slow by 1 step and we have to move fast by 2 steps. Tortoise and hare algorithm. That's what the algorithm states here. So fast, I'll just give here square sum of here fast. This is fine. We are moving slow by 1 step and we are moving fast by 2 steps here. This is fine. The next step here is if fast reaches 1, then it's a happy number. So we have to return here fast equals 1 directly. we are checking whether fast is 1. We are comparing here, right? We are making use of the comparison operator here. So I hope this is clear. This is it for the code. Let me format the code once and let me hit the run button. So I hope this works. Let's see. So what happened here? Wrong answer. We have to get here true, right? We are getting false. So let's see what we have done. So here, what mistake I have done is in the square sum, this one function, helper function, whatever we are considering here. So in this one, we have to return the computed sum, right? So this one I have not returned anything here. In a hurry, I just went into main function, I think. So this is fine. Let me format the code once and let me hit the run button again. I hope this works now. This has to. Let's see. Yeah, you can clearly see here the sample test cases are getting passed here. Let me hit the submit button quickly. So here, let's hope this works. Yeah, you can clearly see all the test cases are getting passed here. Means the code works absolutely correct on this case. So let's quickly discuss the complexities for the code that we have written. So the approach that we went with here is Floyd's cycle detection or the tortoise and hare algorithm. We know this one, right? So what would be the time complexity here? The overall time complexity would be here big O of logarithmic n. Why it is log n here? Each iteration reduces the number significantly here. So instead of big O of n here, so the overall time complexity would be big O of logarithmic n. So I hope this is clear. What would be the space complexity here? The overall space complexity would be big of 1. Why it is big of 1 here? Because we are making use of only few extra variables. You can clearly see slow and fast mainly here. In this case, we are making use of sum. So sum num. So here we are making use of the few extra variables which requires constant space. We do not require any extra space here, right? So the overall space complexity would be big of 1. The time complexity here is big of log n and the space complexity here is big of 1 in this case. So I hope the solution or the code that we have written is completely clear. For now, this is it. Thanks for watching, guys.